Hello everyone! Today we shall be covering our second fluid mechanics lesson, which is forces on a submerged surface. So, I have some surface here that is red, that is submerged, and you'll notice here I have this triangle on top of my fluid line. That just means that above the fluid line is open surface. That just means it's open to the air. So here is my submerged object, my actual surface, and here is my projected surface. And whenever we are trying to find the hydrostatic forces on objects, we always use the projected surface. So what is the forces on a submerged object? Well, Fr is called the hydrostatic force. Hydrostatic force. And to find this force, we need to deal with the fluid pressure that's on this object as a result to its depth. So, well, we know the pressure at a given depth is pressure is equal to rho g, and then the height of the fluid, here h. In this case, I have my plane here to the surface. I want everything to be perpendicular to this plane, so I'm going to turn h into y sine of theta. That way, whatever point I'm mapping here, I will do with respect to whatever angle it has with the surface. So my pressure becomes rho g y sine theta. And then if you recall, my computer stops freezing. Recall, the derivative of the force is equal to pressure dA. We're going to assume that the pressure of the fluid, the pressure up here is constant, not going to change. So, or with respect to area, this horizontal, which means the fluid pressure at a given horizontal distance or depth does not change, it is constant. So if I am at 5 meters, no matter where I am horizontally, my pressure at 5 meters is constant. So the force at that depth only corresponds to how much area I have exposed. So we integrate that with respect to A. I get force is equal to the integral with respect to A of, remember, pressure is Pg, y sine theta. And if I'm assuming, dA, if I'm assuming this plate up here is not turning, my theta is going to be constant, and gravity is constant, and my density is constant. Here, I'll change this P here to be looking more similar to rho. There. So let's do the integration. Pull everything out that we know. So rho g sine theta times the integral of a y dA. Now, if you recall the centroid of an axis, so recall centroid of an area, we get, I'll just do this in blue. Y of the centroid is equal to 1 over area, integral area of y dA. Now, doesn't this look very, very familiar to this? Therefore, force is equal to rho g sine theta times the multiply area over area of the object times the depth of the centroid along this axis that is parallel to my surface. And then this would be, and then if you notice here, there we go. So let's simplify it even some more. Well, if h is equal to y sine theta, that means height of the centroid must equal to the y of the centroid times sine of theta. Therefore, I can do rho g times the area times height of the centroid, or depth of the centroid. And this would be my hydrostatic force. And if you know, well, my pressure equation here is rho GH, and this is rho GHC, which means the hydrostatic force is also equal to the pressure at the centroid times the area of the plate. So, well, now we know the forces, but where is it located on the plate? Where is this going to be? It might be at the centroid, it might not. Depends on the orientation of the plate and the different type of shapes you have. So, let's find out where it is. Well, if you know physics, if there's a force and there's a reference point, there is a moment. So if I set my reference point here at the surface, I can take the moment about this point caused by the hydrostatic force on the plate. Well, from this point here, I'll do a different color. From this point here to the location of the force is going to be some distance y from the surface. Well, let's find that distance y. So I have up here dF is equal to rho g sine of theta times y dA, because don't know where my y is quite yet, so it's a variable. And then I have my moment equation, if you recall, is equal to my lever arm length times my force. So dm is equal to rho g sine theta y squared dA. Integrate both sides. I have my moment is equal to my integral with respect to the area, rho g sine theta y squared dA. So then pull everything out. Moment is equal to rho g sine theta integral with respect to the area, y squared dA. Now, if you recall, moment of inertia for an area, I'll do it over here. Call moment of inertia, you get I sub x is equal to the integral from a of y squared dA. Well, isn't this familiar? You're going to get that a lot in this video, by the way, to this. So therefore, my moment is equal to rho g sine of theta Ix, or moment of inertia about the x-axis. So there we go. Now I know the moment caused by this hydrostatic force on the plane. But remember, I want to know, where is this force located? Well, my moment is of the resolved hydrostatic force is going to be Fr times its location from my point O up here, point O, is equal to rho g sine theta I sub x. Now, I sub x, or the moment of inertia of x, is not the moment of inertia of the centroid. It is the moment of inertia caused by where my new point is, so I'm going to have a shift from the center, therefore I'm going to have to use the parallel axis theorem. So, I sub x is going to be to the moment of inertia about the central axis, plus the area times the distance from the central axis squared, because I am taking the moment from here instead of the center of the plate. So I need that distance. So plug this in. F sub r, y sub r is equal to rho g sine theta times moment of inertia of the axis about the centroid plus a y c squared. Now again, recall the force of the hydrostatic force is rho g a hc, and hc is yc sine theta. So I get rho g yc sine theta times the area is equal to rho g sine theta times ixc plus ayc squared. Well, stuff's going to cancel out now. Rho g cancels out, rho g cancels out. Sine theta cancels out, sine theta cancels out. So I get, oh, I forgot about the YR over here. So I get YR YCA is equal to IXC plus AYC squared. I want to know what YR is here, so solve for it. YR, when you end up solving for it, you get YC plus IXC over YCA. So this is the position of where the hydrostatic force is located relative to the surface along the plane that is parallel to the surface I'm interested in. Alright, so this plane here. Alright, so now we're going to do some example problems on how to apply the hydrostatic force. I will see you in that section of the video. Alright, so here I shall be doing the example part of it. So here I have a wall with a curved surface at the end, and it has a radius r. I want to find what's my hydrostatic force and where is the center of the force located, or center of pressure located. So let's find that out. So I know my equations are Fr equals yc rho g sine theta times area. Well, first things first, I need to find out what is my my projection. So, well, if I'm looking at the projection, it's going to be a flat plane, and if you notice, it is perpendicular to the surface. Therefore, theta is equal to 90 degrees. Alright? And so, let's plug that in. I get Fr is equal to yc rho g sine 90 degrees is 1, so A. Now, YC is going to be the center of that projection, which is a line. So, it's just going to be the center of that plate, and it's going to be that depth from the surface. And you'd be given that could be 3 feet, 10 feet, 20 meters, doesn't matter. Once you know the depth of it, you're good to go. The next is the area. Well, what area do I plug in? Well, this is a rectangle. So, it's going to be the length of the rectangle times the width of the rectangle. Let's say it has a width of W. So it's going to be FRYC times rho times gravity times the radius times the however depth it is, W is. And then how do I find my location, Y sub R? Well, I go up here to this equation here, and I have it as, let's see, where am I here? I am equal y sub c plus I xc over yca. This is a plate. I know what my yc is because I can just determine it from the top of the surface. Found that out for the force. And I can get the moment of inertia about the center axis from the moment of inertia equation of a plate. And again, yc and area is determined here. Therefore, I know my I actually made a mistake. This is not the hydrostatic force. Notice I have a force horizontal going on, I have a force vertical going down. So the hydrostatic force is actually the horizontal component plus the vertical component, each squared. I'm finding the resultant force of it. That's going to be the hydrostatic force. Well, therefore this equation here is not the hydrostatic force, this is the horizontal force on the plane, on the quarter circle. Therefore, if I plug this equation here, into my horizontal force equation, that will help me determine the hydrostatic force. But you'll notice here, I am still missing the vertical component, this component of the force. How do I determine that? Well, the vertical component is just simply the weight of the fluid, rho v g, where this symbol here is the volume of the fluid, and well, because we use v to be the velocity of fluid. So just putting a line through it lets you know its volume is just nomenclature to keep your equations from being confusing. Well, that's how you do it on a curved surface. But we want to do it for, since this is a special case, what about a general case? We just had some plate. Well, if I were to go up here, I know what my density of my fluid is from this equation. They would give it to you. You know the acceleration of the gravity of your planet, usually it's Earth. HC, like I said up here, would be the center of your object. Your centroid of your object could be quarter circle, half circle, doesn't matter. Each object would have a different centroid. But what about area? What's my area? Down here, it was a rectangle when this was a quarter circle. Does that mean my areas up here will be rectangles? The answer is no. This area here in this equation is going to be the area of your plate. So even though my projection would be a line, my area would be whatever shape that plate is. So if my area is a if my plate is a half circle, my projection will be a line, but my area will be pi r squared over 2. Triangle equation, your area is the area of a triangle, 1/2 base times height, so on and so forth for each shape. Only the quarter circle dome here has a special case where you have to do the horizontal and the vertical components to find the resultant hydrostatic force on the shape. Thank you for joining me tonight. Let me know if you have any questions, and I will answer them in the comment section. Thank you very much.